But to introduce ourselves into Unit 3, we're not going to start with just jumping right into trig, the kind of trig that you learned in geometry class with SOHCAHTOA, sine, cosine, and tangent. We're going to talk about what these actually model in real life. Now, periodic functions, which is what all of our trig functions are called, a periodic relationship between two variables occurs when the output values demonstrate a repeating pattern over successive equal length intervals. Let's highlight the word repeating pattern. That's what we're going to be looking for and working with for the next unit, is functions that repeat themselves over and over again. So the first and major vocabulary word for today is the period of a periodic function. The period of a periodic function is the length of the x values that it takes for the function to complete one cycle and start repeating itself again. So if we look at this graph up that we're given for f of x in this example 1, it says the function f is periodic with a period 4. Let's figure out what that means. Since it says that it has a period of 4, do you notice that this shape, going up, going sideways, going down, starts to repeat after 4 specific units? 1, 2, 3, 4. That is a period of this function. Every 4 units, the shape is going to repeat. So the next 4 units, we have up, then sideways, then down. Let's do 2 more. We're going to graph 2 more periods, so 2 more of these shapes on this same grid. So we would go from 7 to 9 because it goes up, from 9 to 10 flat, and then from 10 to 11 down. You see how it's the same shape? And then we repeat again. So just making the same shape over and over again. In my head, this kind of looks like an EKG, if any of y'all are doing like med things, like the heartbeat monitor, boop, 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 boop. Your heart should beat repeatedly over and over again. So if we graphed a heartbeat, it would be a periodic function unless you were having some sort of heart spasm, in which case it would not be a periodic function and you need to go see a doctor. But a well-working heart that goes glug glug over and over again is a periodic function. We could graph it if we wanted to. Does that make sense? The idea of a period of a function. Okay. Cool. In example 2, it says a portion of the graph of the periodic function g is shown above. What is the least possible value of the period for g? So again, we're just trying to see how long it takes for that shape to repeat. Okay. When I do these problems, I look for something that's interesting or something that's really unique about the shape. In my mind, it gets unique when it starts turning downwards right here. So it goes down, it goes up, it goes flat. When's the next time it goes down again? Right here. 5. So if we go from 0, which is where I started looking, to 5, that means that the period of g is 5. Now, if you're in physics, you're probably thinking about, well, I don't know if y'all cover this part in physics yet. A pendulum swings back and forth. That's a repeating pattern. And if you have a period of like a pendulum swinging, there is a letter for period in physics. It's capital T. That's the same thing we're talking about, but in this class, we're not using the capital T for period. I get that capital T means period, so if you're in physics and you accidentally write that, I'm going to know what you're talking about, but we're going to write out the word period is 4 or something like that in this class. So try not to use the symbol for period, but I know it exists, so I get it. Now, because these functions repeat, we can use the idea of repeating patterns to evaluate these functions even when they don't show up on our graph. Because if you notice, the very first part of example 3 says to evaluate g of 14. Well, this is g. Normally when we evaluate, we just like read the graph, right? But my graph doesn't extend to 14. But we're going to use the idea of how it repeats to figure out what g of 14 is. If we think about the number 14 and the period of 5, how many times would 5 go into 14? Don't think about it too hard. How many times does 5 go into 14? 2. So this is like saying g of 2 times 5 plus how many left over? 4. So we would have 2 complete periods of the function, 2 times 5, and then 4. For our sake, that means we're really just reading the graph at g of 4 because it's going to repeat itself every 5 units. So we could just look at g of 4 and say that that's the value. And what is g of 4? 7. How did we get that? We looked at 4 on the x-axis and went and read the graph. It's at a height of 7. So g of 14, which is like g of 4, is 7. See how we can use the period to estimate what's going to happen in the future? Okay, what about g of 72? How many times does 5 go into 72? Oh yeah, we have to think about that one. 14 times, so this is going to be 14 times our period. So we'll repeat this pattern 14 times with how many left over? 2. 5 times 14 is 70, 70 plus 2 is 72. So really, we would repeat the pattern 14 times and then move 2 more spaces forward, which means g of 2 would be how much? 6. Very good. Let's put a little box around this guy. Again, I'm giving you the challenging one because it's negative, but I want you to try part C. Think about what you can come up with the same idea. There's 2 ways to solve this, by the way, that I did both, so we'll see what you come up with. You've got people next to you. Let's talk it out. Okay, I'm hearing some good discussion because I hear us talking about negative numbers. That is one of the ways that I did this, so I'm going to lean into that way since I heard that discussion. If we think about how to multiply 5, our period, to get negative 17, in my head, my brain did this. If we do 4 times negative 5 or 5 times negative 4, we would be at negative 20, correct? Yeah. If I need to get to negative 17, what do I have to do? If I'm at negative 20? Add 3. Now, again, this part represents the repeating period. So that part essentially goes back to normal. Goes back to the beginning. So we can say that g of negative 17 is the same as g of 3. And the g of 3, if we read the graph, is 7. Now another way you could do this is you could evaluate g of negative 2, because if you look at your graph, you do have negative 2. There was a way to work it that way. So if your paper at some point said g of negative 2 and you read the graph, that's also correct. Did it work the way you were thinking? Cool. Love it. If we look on the back of this page, I don't have to just provide you with a graph to be able to answer questions like this. We can also be provided a table. Now, tables don't normally make us think about periodic functions, so we look at the blurb next to the table. It says the graph of h is periodic with a period of 5. So that's important. This is technically a different problem, but it does still tell me that the period is 5. So we're going to be using the same number to do our period here. It says the values of h shown at selected values of x. Find the following values. So we're going to do first h of negative 2. Well, negative 2 is very obviously not in our table, so we're going to have to make it work. What would I have to multiply 5 by to end up getting to negative 2? So if I'm doing this like I did on the front, this would be h of what times 5? Okay, I heard 1 times negative 5. Cool. Which would mean I'm at negative 5. My pattern starts repeating. What do I have to add at the end? Plus 3 again. So we're saying that this is the same as h of 3. Well, h of 3 is in my table. What is h of 3? 0. So again, you're trying to figure out how many of the periods you would need to get within 5 plus or minus of the number that you want. This is technically called modular arithmetic, which you will not actually learn about until college, but if you've ever thought about code making and code breaking, like they did in the war with the Enigma machine, this is the math that is involved in doing it. Modular arithmetic. You don't need to know that. It's just one of my favorite kind of maths. I'm going to leave you with B, C, and D to work so that I can walk around and answer some questions. So you've got B, C, and D to try. And yes, B and D are a challenge, but you got it. I mean C and D. All right, let's chat. I'm seeing some good stuff. Yeah. Number B, if we do h of 6, my brain says, well, that is 1 times 5 plus 1. And since every 5 it repeats, it's like I can just say this is h of 1. And h of 1 is negative 2. I got that from the table. How do we do on that one? Fabulous. Did we remember about number C, that is a composite function? So we're going to have to put a function in a function. When I did this problem, I left the h on the outside alone and then just did what we had done on all the other problems for the h on the inside, which means this would be 1 times 5 plus 4, which is the same as saying h of 4 right? Because every repeating 5s, we start over. H of 4, based on my table, is 3. Well, now my problem, since I left the outside there, says H of 3, which is what I need to do now. Luckily, 3 is in my table. What is H of 3? 0. So yes, you just had to do it twice, but luckily the number we got as our output was straight up in the table, so we didn't have to do extra work of shifting the period. Now part D kind of conceptualizes this further to any period, basically. It says to evaluate h of 5k minus 3, where k is an integer. An integer is just like any plain number. The symbol for integer, which you're going to be allowed to use on the test, looks like this. It says fancy Z. It's kind of like, you know how that fun and funky R for all real numbers exists? Integers is this symbol right here. So if you would like to switch to using that symbol anytime you want to write the word integer, I get what it means. The test readers get what it means. Or you just write out the word integer. An integer is a whole number, for lack of a better word, because that's actually something different. But it's going to be non-fraction, non-decimal, some sort of whole number. 0 is included and negative numbers are included, which means it's not technically a whole number, but that's a whole other question. So basically we're saying we can plug whatever number we want into this function here, and we're going to evaluate it. But since our period is 5, it's just like all these other problems where we had this period of 5 written in our problem. So really, this is just like saying that this is equal to h of negative 3. Now, h of negative 3 is something I can solve. H of negative 3 is like 1 times negative 5 plus 2, right? Because negative 5 plus 2 is negative 3. That means this is just like saying h of 2, and that is not in my table. LOL, what did I do here? I know what I did, but I want you to figure it out. What did I do here? How do I figure this out? Because h of 2 is not in my table, even though that's within the first period. What's in your table that's very similar to h of 2? 7, because isn't 1 times 5 plus 2 7? So this is the same thing as h of 2. So we can evaluate this at 2. Because every time there's 5 units, your numbers repeat. So at 2, at 7, at 12, at 17, at 22, every time we repeat a 5, we're going to have the same value of 2. That is a periodic function. Yes?
How did you go from 4 to 3 on letters?
How did I go from 4 to 3? Oh, great question. Okay, so h of 4 is in my table. So h of 4 is 3, so I can replace all of h of 4 with the number 3. It's like a normal, like, that would have been our answer in another problem. We just had to do more on that problem. Okay, cool. So since we're starting to talk about this phenomena that repeats over and over again, this periodic function, it's helpful to have some sort of notation. Basically, since it's repeating itself over and over again, if we shifted the graph by its period, it would land right on top of itself over and over again, since that little chunk of pattern repeats every time. So in example 4, the one above, the period of h was 5, meaning that we could translate the graph of h horizontally 5 units and end up with the same graph. That's exactly how we were able to do the 5 times some number, some integer, plus or minus a number, and evaluate the function. So when we're working with these functions all semester, all the rest of the quarter, know that they are just translations of themselves, scooted over, scooted over, scooted over to repeat the pattern. Which means, if we took example 5 here, it says the graph of f is periodic with a domain of all real numbers. It's not shown all real numbers, we're only shown from 1 to 9, but it's telling us it repeats for forever. 2 full periods of f are shown. Find all the input values of f that yield an output of 1 unit. Okay. It's a lot of things that we don't understand yet. I get it. Here's 1. How many times in my 2 periods did I touch 1? 2 times, okay? And since there are 2 periods shown, I'll highlight each of the periods. So this is 1 period, and this is another period for this function. How long is the period for this graph? Okay, so we're going to say the period is 4. That's how many units it takes before I start repeating the pattern. From the beginning, so thinking of starting right here where the pattern starts, how many units does it take for me to reach the value of 1? If we start at 1, the value of 1 appears at 2, so how many units did that take? If we start here and we get to here, how many units is that? 1 unit. Okay, great. So we have 1 unit after every repeating period when we get to the value of 1. So we're going to say that all of the values of x are going to be starting at the number 2 and then repeating every 4 units. Because 1, 2, 3, 4 units away from 2 is 6, and that's the next time that we get the number 1. So this is going to be 2 plus 4k. That's showing me that every period it repeats. But we have to be sure we explain to the reader, or explain to me what k is representing. So you're going to say where k is an integer. And I'm going to use the integer symbol because integer has too many letters for me. So again, it's a weird explanation. Let me try one more time. We noticed that the first time was 1 unit past the beginning of my period. Starting at the value 2, that is the first time I see that we hit 1. The next time that we hit 1 is 1, 2, 3, 4 units away. So my period is 4. Every repeating 4, I'm starting at 2, I'm going to get the value I want. Okay, if we were to change this problem and I asked you not the output value of 1, but the output value of 4, how would that change one of the numbers here? 2 would go to 1 because the first time I see the value of 4 is at the x value of 1, the beginning of my period, which happens to be starting at 1. Okay, we'll get more practice with this because when we start graphing sine, cosine, and tangent, we'll start talking about the repeating zeros and the repeating maxes and mins. So if this weird thing that I just wrote with the k in it is not comfortable yet, we will get comfortable. But what we also need to get comfortable with, flip the page, is some of the ways that you're going to be asked an FRQ on this test. So for an FRQ number 3, it is always going to look like this. So you can get very comfortable for the FRQ for this test. Number 3 is going to have some scenario like this. This is not all of the questions for FRQ number 3 because we haven't covered some of it, but it's the parts that we're going to be able to understand. Now, this is a real-world scenario with a periodic function. It's always going to be a real-world scenario with a periodic function. It's always going to ask you the same questions, which is very nice. This question says, the figure shows a large clock mounted to a vertical wall. The clock has an 8-inch long moving minute hand. The center of the clock is 120 inches directly above the floor. At time t equal to 0 minutes, the minute hand is pointed directly up at the 12. However, the clock is not working properly, and the minute hand is moving twice as fast as it should. Thus, the next time the minute hand points directly up to 12 is at the time t equal to 30 minutes instead of 60. As the minute hand moves, the distance between the endpoint of the minute hand and the floor periodically decreases and increases. Now this makes sense because if I was following just the minute hand, it would go up, it would go down, it would go back up. So it makes this repeating pattern that looks like this over and over again if we were to graph it. That's a periodic function. The periodic function h models the distance in inches between the endpoint of the minute hand from the floor and the floor as a function of time t in minutes. Okay, let's label some stuff because I think it's going to be helpful before we move on. On your clock, how long is the minute hand? 8 inches. It gave us that in the blurb. It's going to give it to you in the blurb. It's also going to tell you how high the center of the clock is. How high is the center of the clock off the floor? 120 inches. Okay, those are important things to find in this problem. We needed to know 8 inches long is the lever that's moving, and the clock itself is 120 inches above the ground. We also need to know the period of this, which means we need to know how long it takes for the minute hand to go from the top down and end up back up at the top. What does this problem say is the period for this function? So when is the first time it goes back to being at the 12? 30 minutes. So my period is going to be 30 minutes. So we'll say period is 30. Okay. Part A. And again, part A is always going to look exactly like this and ask you the same question, which is really, really nice. It says 5 points F, G, J, K, and P are labeled on the graph. No scale is indicated, no axes are presented. Determine possible coordinates, time, and height for the 5 points F, G, J, K, and P. If we're looking at F, what do you notice about the point F when you look at like this wavy thing? It's the top. Where is our clock at the top? Or sorry, let me rephrase. When is our clock at the top? At 12. Okay, well 12 is the location. When? At 0 minutes. So we can say that first point, F, is going to be at time 0. H of t is a height, like in real life height. So don't say 8. How high is F off the ground? 128. Where'd you get the 128 from? Yeah, the center of the clock's at 120, and it goes up 8 more to reach the top of the clock. It's at 128. Okay. Let's go to the next easy one. I'm going to label all of these, but in my opinion, the next easy one is P. Why is P the next easy one in my opinion? It repeats, but it's not at 0 anymore for time. This is the first time it starts repeating. So how long should that take? 30 minutes. So we're going to say 30, 128. That's the first time it's made it back to its starting point. Now, if a periodic function has to be done smoothly, what do you think this time is going to be? The J. 15. Very good. Halfway between it, yeah? So we're going to say J is at 15 minutes. What is its height? Okay, let me help you out. Okay, so we said that this was going to be 128 and 128. We said this is going to be 120. What does that mean J is? 112, because it's 8 lower than the center. That lever hand goes down. So we're going to have 15, 112. Okay? In my opinion, these ones are a little bit more difficult to get based on this picture. What's the time going to be at G? 7.5, 7 minutes and 30 seconds, 7.5. What's the height going to be? 120, just that center line since it's on the center line. What about K? What is the time? 22.5, 22 minutes and 30 seconds, and again at a height of 120. That is exactly how one of your FRQ questions is going to be. A different scenario. Literally, it will give you this picture with these exact words typed in it. Pretty good, right? We can read it. We can read this scenario, figure out how tall it is. Now, for part B here, this is actually going to be part C for the actual FRQ. We're skipping actual part B because we haven't learned stuff about that yet. But for part B, it says refer to the graph of H in part A. So we're talking about this graph right here. The t-coordinate of G is T1 and the t-coordinate of J is T2. On the interval from T1 to T2, which of the following is true about H? Take a highlighter right now, and I want you to highlight the graph from G to J. So we're talking about this interval right here. T1 to T2 is from G to J. What is happening with that graph? Is it increasing or decreasing? Decreasing. So let's cross out the ones that say increasing because it's definitely going down. The next problem of this is that it says H is positive and H is negative. Now, I'm sure your brains are thinking about concavity. I love that. This question is not asking about concavity. It's asking about, in real life, is this clock, is this lever arm above the ground or below the ground? Is it hanging on a wall or is it like buried in the earth? It's above. It's always going to be positive because the clock is on the wall. It's up. It's above the ground. So the correct answer here is H is positive and decreasing. So we could actually just straight up get rid of the two that say negative. Our clock is always above the ground. Now there's a scenario that I've seen already out there in the AP world where it's a roller coaster. No, sorry. What's the thing?
Ferris wheel.
Thank you. Ferris wheel that partially goes underneath the ground. Half of it is above, half of it is below. So it's not always literally every time going to be positive, but our clock is above the ground. So our clock is at a positive height. So when it's talking about positive versus negative, we're talking about in real life. That's not how you spell that word. Negative. In real life. That's going to be really important for you to remember. We're talking about in real life. The increasing, decreasing part was really easy because you could just look at the graph to see if it's going up or going down. Now we will recall in part 2 here the idea of concavity. Part 2 says describe how the rate of change of H is changing. A changing rate of change is asking about concavity. So that section that we highlighted in green, is it concave up or concave down? Concave up. Write that down for yourself right here. This is concave up. That means, and the sentence we're going to try to start writing is, giving it some details, on the interval from T1 to T2, the graph of H appears to be concave up. Okay, appears to be concave up. So the rate of change is increasing. Now remember, that's kind of weird because we just said that the graph is decreasing. That's the graph decreasing. The rate of change is increasing since it's concave up. So concavity has to do with the rate of change or the slope. Anytime you say concave up, the rate of change is increasing. Anytime you say concave down, the rate of change is decreasing. And we've done that multiple times, but you need to write it down for yourself again. Concave up, increasing rate of change. Concave down, decreasing rate of change. Now, obviously, that whole sentence would be the ideal answer. I'm pretty sure that readers will accept it if you say the rate of change is increasing because it's concave up. That's as blunt as it can get. But this is the nice flowery language we like to use here.